And yeah, it's on physics-informed/enhanced. We'll see the difference in a bit. Neural networks. So I'm doing a PhD at EPFL, just one floor below in the lab of Martin Viterli. Kevan is in the IMOS lab. Who's the professor? Who? Olga Fink. Okay, Olga Fink. So we're going to talk about two approaches to physics-informed neural networks, because it's more of a technique you can think of, and then it gets to become very application specific. How many people have heard of this term before? Used this technique to some extent? Okay, cool. Quite a few of you. So essentially the motivation for this approach is if we consider classic supervised machine learning. So this is the case where, let's say, we have an input of, or a data set of inputs and outputs. Maybe we're trying to learn some sort of tunable function that goes from the inputs to the outputs. So the most simple case would be we use linear regression. And yes, linear regression is a form of machine learning. That would be a very simple case. Maybe more of the hype these days is to go towards deep neural networks, for example, a ResNet. And one of the caveats of just using linear regression is that it's too simple. Maybe it's not going to model perfectly or well enough this input to output pair. And my animations were kind of broken. And you probably saw the caveat of deep neural networks is you could risk overfitting in these cases, or it may not generalize to new contexts. So typically techniques to address this overfitting would be, okay, maybe we simplify the model. We go back towards the simpler linear regression, maybe not all the way towards there. That could be one technique. Another could be regularization, maybe on the weights with L1 or L2 norms, or doing dropouts within the neural network. Another approach maybe would be, okay, maybe you need to collect more data. Either you actually collect it, you simulate it, or you do augmentation techniques on the data that you have. But the theme of this workshop is how can we use this physics-informed approach to address overfitting or to improve generalization. And the basic idea is that, okay, imagine you're working on a situation, and we'll give some examples in just a bit, where the underlying problem is some sort of physical or biological or chemical process. So we probably have some model, maybe even a basic one, that can describe this. And the idea is we want to embed this information into the learning process, rather than just blindly taking input-output pairs, trying to fit it to a neural network or to something simpler like linear regression. Let's try to embed these physical, biological, or chemical laws into the process. Yeah.
But when you do machine learning, isn't the point that you're trying to model the phenomena? If you already have the model to embed,
I guess you're trying to do it by you're hoping your data represents that well enough, right? When in a classical machine learning sense, like you hope that, okay, you're learning this particular camera or learning how this particular microphone works, but you can actually input more explicitly that information into the learning process. Because if you're just using the data, you're hoping that this highly parameterized neural network will be able to learn these laws, but you can actually incorporate the laws more explicitly. So we'll give a few examples, but hopefully that gives the difference a bit. So yeah, some of the advantages, so kind of mentioned before, but one of the nice ones is that it can encourage or limit the solutions now for our learned function to a space that adheres to these physical priors or physical laws. And maybe it also allows our solution to be more interpretable as well too. Another advantage is that it can require less data than just naive neural networks, where you maybe have to throw many input-output pairs. Maybe incorporating these laws can constrain it a bit more. And we can actually take it even a step further. And let's say we have some simulation, some physical laws, some model of our process within our learning function. We could actually try to learn hyperparameters. Let's say if we have a lens, maybe we want to learn the shape of that lens, the function of that lens. If we have other types of physical parameters, we could try to learn those in simulation and then recreate that physically. We'll come to some examples in a bit. So traditionally, physics-informed neural networks, or PINNs, as they're known more shortly, they were made. This concept was more well known in the field of solving partial differential equations. Some of the work where I've personally seen it or worked with it more as an audio context, where maybe you have like a speech recognition system like Alexa or Siri, and you can model the acoustic propagation within a room, and you want to maybe learn the processing and also maybe some hyperparameters of your simulation along with actual speech recognition itself. Or you can use it in more biological contexts. So in neuroscience, there's this thing called the connectome, which you can measure all this connectivity between neurons in, let's say, a fruit fly. And let's say you want to use that information to figure out, okay, how does a fruit fly react to or what's its activity in different stimuli? Because a connectome is a very static thing, but then how can we use that static thing to constrain how it does kinetic things? These are just very high-level examples. My specialty is definitely not in this, but it's an interesting example where I've seen it in a more biological context. But yeah, today we'll see it in Kevan's work where he applies it to energy distribution, and he'll give some of the context and background for that. And then I'll talk about it in more the, let's say, the imaging context. And one annoying thing, but as Peter said, one motivation for these talks has been to kind of give you the intuitive approach to it so you don't feel maybe overwhelmed by things. Because it can feel overwhelming for Physics Informed because there's very application-specific stuff that you may need to know. But if you can just keep in your mind the general idea, okay, how am I incorporating my biological, physical, chemical info into a learning process? That's essentially the main idea. And what we're here to do is just kind of show you some examples of that. So with that, I'll hand it over to Kevan, unless there are any questions so far. Okay.
Okay. Hello, everyone. Thank you, Eric, for the nice introduction, and also thank the LauzHack organizer for inviting me. It's such a pleasure to be there. And before starting to talk about in details about physics informed or physics enhanced neural networks, I want to mention that this part of the presentation is heavily inspired by this paper from Alice Ciccarello. It's published recently, and if you are interested in this topic, I really suggest you to go and take a look at this paper. And now, as you probably know, I'm in the PhD student at IMOS lab, and in the IMOS lab, we decide to tackle some challenges that happen. For example, we all know that the system complexity nowadays are increasing significantly, and also since the complexity is increasing, the data-driven and deep learning-based models are the potential solution for that. However, the generalization ability of this data-driven model is very questionable. And also, since we are working with different industry sectors, so there are some domain experts that provide some domain knowledge about the process. And now we are interested in how we can integrate this domain knowledge into the learning process. Now, for developing the monitoring models, we can divide or categorize the models into two different categories, physics-based model and data-driven model. For example, for physics-based model, we have input data and we have some algorithm which comes from our domain knowledge or physics knowledge that we have. And finally, we can calculate the output data and then take a decision about the model. Also, there is another type of the model which called a data-driven model, which means that we have some bunch of input and output data, and then our main goal is to learn the algorithm to solve these specific tasks. However, each of them has its pros and cons. For example, the purely data-driven algorithm can be dangerous. As Eric mentioned, for example, if we use the simple models, for example, such as linear regression, we have the problem of underfitting. Or if we go for the very complicated model, we have the overfitting the problem. And we know that usually we obtain the model by optimizing on the training data. And even, for example, in the overfitting, we have the very good results on the training data, but we are not interested in this. We are more careful about the performance on the test data. And then usually when we have the overfittings, then we have the poor generalization or poor extrapolation. And also another problem of the all purely data-driven model is that maybe the prediction is not physically consistent. So then the prediction maybe is implausible, which we want to avoid. And also there are some implicit assumptions when we use the data-driven model for the available data. For example, first we assume that the data it's self-informative, which means that these faulty conditions of the, for example, industrial asset can be distinguished well from the healthy condition just based on the data. And also we assume that the data itself is very accurate, which means we have high signal to noise ratio or low noise, or also the sensor are very calibrated. And also the other thing that we need to consider is about the reliability of the data. For example, assume that you take a measurement from one condition, and next time, if we take the measure from the same condition, would be data is the same or not? And so we can conclude that the data-driven models are good, provided that the data itself is good. But it's not useful in this case, usually in the engineering application. For example, not all condition can be observed or labeled. For example, in our lab, we usually do some fault classification on the machines or other kind of industrial assets. And it's very hard to find all kind of faults that can happen on the machine. And some fault can be new. So providing or collecting this data and labeling can be impossible, simply, I can say. And also in some assets, data can be very expensive to collect. And also maybe we have some heterogeneity of that. And also we need to consider that data should be up to date and also should be in high quality, as I mentioned. But until now, I criticize about the purely data-driven model. But I can also say that the physics-based approaches can be also dangerous. We know that the physics models, usually they have a good generalization, but they are expensive and they can have very high computational costs. For example, the inference time can be very long. And this is very important when we want to have some real-time prediction. So the physics-based model cannot be very well in this situation. And also, we know that the physics-based model, usually the prediction comes from them are physically consistent. But in the complex system, since for the modeling the complex system, we have to do some simplified assumptions, maybe the prediction is not correct. And also, we know that the uncertainty is not inevitable because this uncertainty can come from the data. Sorry, you have a question. And as I mentioned, each of these methods has pros and cons, and that's why we are interested to combine both of them to have the physics-enhanced machine learning model. And in particularly in the engineering application, the amount of the useful data for the complex system is limited. And then also in the small data regime, we are very interested in generalizability or approach. So for this reason, we need physics knowledge to enable this thing. And you can take a look at this figure. For example, if we have a lot of data, but no physics, definitely the reasonable thing is going for purely data-driven. Or we have a lot of physics, but no data, okay, it's reasonable to go for physics. But in many cases, we are lying at the between. So that's why physics enhanced can be useful in many cases. And now, when we talk about the physics-enhanced machine learning models, we need to also talk about the bias that we can incorporate into the learning process. Usually, we categorize the bias into the 4 subcategories. For example, for the first one, we can call it observational bias, which means that we just augment our data set with the other data that embody underlying physics. Or the other kind of bias is learning bias. For example, we can design a specific loss function for that or develop a specific optimization algorithm for reaching the better model. Or the other thing can be inductive bias, which can refer to your architecture itself. For example, if your data set has the spatial correlation between each entity, we can go for the graph-based approach. Or for example, if your data set is an image, we can go for the CNN architecture. And the other kind of bias is about model form or discrepancy bias, which means that, okay, we know some PDE equation or partially known, and now we want to incorporate in our model. So as Eric mentioned, why do we need this? Because we have the huge space for the solution. But when we add this prior knowledge, we can restrict the region, and then we can help the model to go into the correct solution. That's why we are interested in incorporating this prior knowledge. So the one good example about the physics-enhanced model is physics-informed neural networks. And then in this picture, you can see that at each part, we can add different kind of bias. For example, assume that in our data, we have some input data, but we add some another kind of data or augment some data based on some physical knowledge. Then we can see that we have observational bias here. Or usually in a purely data-driven, we are just care about the output layer, the value of the output layer. But if we have some information about the PDE of the process, okay, we can use the auto-differentiable operator, and now we can make the PDE of the output. We constrain the output with this PDE. And here is also discrepancy biases that I mentioned before. And now based on this PDE, we can incorporate it into our loss function, for example, as a regularization. So we can say that, okay, this is the learning biases we have. And finally, we can see that here we use the neural network architecture. This is the inductive bias. As I mentioned, it really depends on your type of your data set. For example, in this talk, I will cover about the sensor networks. And since we have the spatial correlation among each sensor, we are more interested in the graph-based approaches. And there is one example, which means that it's not necessary to be reproducible, but it's a very good example for visualization, at least for the learning of why the physics-informed neural network is good, but it's not necessary to be very correct. For example, you have the problem, which is the damped harmonic oscillator. And now we have some points from your data, for example, here. And now you want to fit the model, you want to fit the model to make the prediction even for the next step or do some extrapolation. Okay, if you do just purely data-driven or purely neural network, you can see that our model can do interpolation very well, but in the generalization, no, it's do very bad. It cannot fit very well, or it's very bad. But since we have some information about the equation of the damped oscillator, we can incorporate it as a regularization into the loss function, and then we have the better generalization. For example, we have the better extrapolation. Here, the reason that this neural network works not very good because we have some knowledge, but we drop this. So that's why it's just good at the interpolation, but at the extrapolation, it performs very bad. No? Yes?
I have two questions about the previous game. So the number of steps is very different. Is it because
Yes. No, that's why I say that this GIF is not necessarily good. Yes, it's just two examples to show that. Yes. Yes. Now, based on this explanation in the engineering application, this is one question, that how much data and physics should be included in the model, and also how we can include this domain knowledge and the physics into the data-driven model. So based on these questions, we arrive at these three subcategories of physics-enhanced model. So we have physics-guided machine learning model, physics-encoded, and physics-informed. But what's the difference between them? You can see that here. For example, if we start with just data-driven model and go toward to physics, we have physics-informed machine learning. What do I mean about this? I mean that the data-driven is the building blocks or the main components of your algorithm, and then you just use physics to guide the learning process. But at the vice versa, when you start from physics and then goes to the data-driven, we have physics-guided machine learning model. And what I mean about this, I mean that you can assume that you have a very high fidelity physics simulator, but there are some parameters that you don't know. You want to calibrate your model, or you want to infer some parameters. Then you can just use the very small real-world data to just infer these parameters. And the other type is called physics-encoded machine learning. That means it's at the union of the both. But maybe you have one question about, okay, we know that we have different kind of physics-enhanced machine learning model, but which one we should use? Okay, unfortunately, I have to tell you that there is no one-size-fits-all solution. So you should take a decision based on the balance between the domain knowledge and the data availability. So, and also the other thing that you need to consider is about the user's purpose. For example, if you want to just build a model to solver acceleration, for example, for PDE, you should definitely go for the physics-informed machine learning model. But if you want to do, and also the other thing that you need to consider about the system complexity, for example, some nature of the system, for example, LTI or nonlinear system or multi-physics can influence our choice. And currently, some physics and machine learning models are struggle with highly nonlinear system and multi-scale system. Now, I will start with a quick introduction to graph neural networks. It's just, I think, 3 or 4 slides. But if you have some question, you can ask me now about previous section. Okay.
So the reason you talk about graph neural networks isn't because they are like a super category of...
No. This just graph neural networks is other kind of architecture because in the one application that we will cover, we talk about the energy distribution network. And the energy distribution network, we have a bunch of the sensors for monitoring the network. And the best choice until now for the imposing the inductive biases is graph-based models. That's it's not related to physics.
So it's just the background knowledge.
Just background, yes.
We're not sure if you know graph neural network, so we just added a couple of slides to
Yes.
give you information about that.
Okay, now I start with a quick introduction to graph neural networks. We know that, or you probably know, but graph neural networks are a little bit different from the traditional neural network. For example, the order of the elements is shouldn't matter. And also the function of the output for each node is based on the neighbors or neighbors of neighbors or node itself. And also depends on the how much k-hop neighborhood you need to consider, you need to add more layer. And we have 3 categories of the graph neural networks. First, we have the spatial-based graph neural networks, which use the message passing scheme. For example, you can see at this figure, you can see that, assume that we have this target, we want to update this node. Sorry, we have to update this node. So each neighbors of this node send a message to this target node. So you can take a look at this figure now. For example, this node has 3 neighbors. So red one, green one, and blue one. So you can see here. And now if you add another layer, you can have access to the second hop neighborhood. For example, the neighbors of neighbors. For example, the neighbors of the red, which are again, this target node and also the green one. And now when this message sent, we aggregate all of the message into the node I, and then we update its state. The important thing that you need to consider is that the aggregation here should be permutation invariant. For example, the aggregate function can be the operator, which means that it should be invariant to each permutation. For example, you can use sum of the message or mean of the message because the order doesn't matter. For example, when you take a mean or sum. And we have other kind of GNNs which called spectral GNNs. Then this idea comes from the graph signal processing. And we know that in the signal processing theory, we can calculate the convolution in the Fourier domain. For example, you can take a Fourier and multiplication and then take an inverse Fourier. And then basically you do the convolution. And now we have this kind of models, but recently these models are not very popular because the main problem is that usually they need eigen decomposition, which is expensive. It can be the order of the cubic, around cubic. And but there are some work definitely to overcome this. And there is another kind of GNN which called attentional GNNs. For example, in spatial GNNs, or for example, the simplest thing in the GNN is called graph convolution network, which say that, okay, all the neighbors are equal to each other. But in attention GNNs, we also assign the weight dynamically into each neighbors. And then we consider that, okay, which neighbor has more importance for our task. And definitely it provides some advantages because it it enhances the expressiveness of the model. So my main message about this GNNs is that in this kind of architecture, we can consider the value of the neighbor for the updating the node itself, which means that, for example, if you have the sensor network, the sensors that are close to each other, we expect that they show the similar value. That's why we are interested in using GNN. And now, yes.
So what Kevin did is something really important research where he's just abstracting what we need
Yes.
from GNN. So you don't need to understand like the absolute details of GNNs. For me also, I don't
Yes.
even know them. We just need to know what he said. Okay, we want to be able to aggregate information.
Yes, exactly. Yeah, the most important thing that you should know is that, okay, GNNs are capable to consider the neighbor's value itself. So that's it. And now we are going to the first application, which is physics-enhanced GNNs for district heating networks. And here our goal is to monitoring the sensor quality of the network. And we know that with the advent of the industrial IoT, we have integrated many smart sensor AI to enhance efficiency in different sectors, for example, manufacturing, energy, infrastructure. And also the decision making is really relies on the data and knowledge collected by the sensor network. But here there are some challenges. First, we usually deploy the sensor throughout the network sparsely because some sensors are very expensive and it's not very useful to put sensor at each places. And also some sensors can be miscalibrated during the time. For example, during the time we can lose the accuracy for the sensors. And also we have budget constraint. As I mentioned, maybe the sensor can be expensive, so we cannot provide sensor for each places. And the other thing is retrofitting existing system and infrastructure. For example, once the system is made or infrastructure is made, it's very hard to go again and install the sensor. So here, our solution is that instead of using the hardware or expensive based solution, we can use the computational based method or computational sensing method. And now we are going for the sub-sensing. But before going, I need to define what is the sub-sensing. In different literature, they also called virtual sensing. And the main goal is to develop the mathematical model or algorithm to infer the unmeasurable variables using the available information that we have. And why it is important? Because sometimes we have incomplete data, and also it provides cost efficiency because instead of putting the hardware sensor, which can be expensive, we can replace this with a software-based sensor or sub-sensor. And also it can help for fault detection and diagnostics of the system. And but there are some concerns and research questions. For example, how domain knowledge can be integrated into learning stage. The solution you should know is physics-enhanced graph neural networks. No, for this, we consider the district heating network, and you can take a look at here. We have, this is just overview of the network that we study. It has power plant, heating plant, and we have 4 buildings, and this is just the layout of this network. And our main task is, okay, we use just mass flow rate sensor to estimate or infer the pressure and temperature of the network. And pressure and temperature of the network is considered as a sub-sensors. So here, this is the proposed method, and you can see that here we have the sensor networks. And for example, you can say that, okay, the red circle are the places that we install the sensor, and we have some value for that. But here we don't have install anything, but we want to infer this value. And in the purely data-driven, we just need to collect the data and just build a model for mapping from a red circle to the blue circle. But we know that in the district heating network, this is very, very well studied from the physics perspective, because for many years people worked on the fluid dynamics or different kind of thing that can satisfy the equation in the district heating network. For example, the thing that we can do, we can use the information about, for example, the pipe characteristic that we have in the network. For example, we can say that, okay, given this pipe diameter or pipe length or pipe roughness, and with the hardware-based sensor, which is mass flow rate sensor, how much we expect that the pressure will be drop or temperature will be drop. Then we can calculate manually and then incorporate as a virtual nodes on the network, which means that we incorporate the observational bias in our system. And then since in the sensor network, as I mentioned, we have the structural data set, which means that we have the spatial correlation between each sensor. We are going for the graph-based model. And then here you are free to choose whatever you want. For example, you can use a spectral GNN or a spatial GNS or attentional GNS or whatever you want. And finally, we have the readout layer and then use MLP to just final mapping. And then we can estimate the values at the unmeasured part, which called our soft sensor or virtual sensors. And now we provide some experiments here. For example, you can see that in almost all cases, the physics enhanced model improved the performance of the data-driven models. Even another thing that you can see from that is that the performance of the graph-based methods are better than CNN or MLP. It's expected because we incorporate the inductive bias by using the GNN on that. And also, we do comparison on the ideal case and the noisy case because usually in the real world, we know at the first what the value of the pipe roughness, but during the time, maybe we have some uncertainty about that because it can be changed during the time. And then we inject the noise on that, and then we reevaluate again, and then we reach the same conclusion that, okay, physics enhanced model can significantly improve the data-driven model in this task. Also, for each sensor, we plot the error. Again, we can see that for almost all sensors, the physics enhanced model works better and improves the performance and by reducing the error. And the conclusion is that, okay, we know that the physics enhanced GNN embed physical laws into the learning, and we have then better generalization to unseen data, and we have the data efficiency, which means that we need less data, and also it helps to have the interpretable or robust model. And in the data-driven GNNs, which rely solely on the data, we can achieve high accuracy with enough data, but may lack physical consistency and generalize poorly on the unseen domain. Thanks. Now I give to Eric for the another application, which is computational lensless imaging. Thanks. Oh, okay. Sorry.
Is this how similar is this to like an observer in dynamics?
Exactly. The soft sensor is for soft sensor, there are different names. For example, they call virtual sensor, observer, and proxy. So they use interchangeably usually.
Okay.
Yes.
So yeah, like observer and control theory, you can do it very
Exactly.
You have the models, so it's easy.
Yes.
It's like learning something.
Yes. Exactly. Yes. Another question? Yes.
I don't think you shared this slide, but I just want to take photos of the first reference setting so that I remember.
Oh, okay. Sure. Sure.
We will send the link to
But okay, you can.
if you release it.
Oh, you're welcome.
All good?
Okay. Perfect.
So yeah, thanks for that. I actually learned quite a few terms now of the physics enhanced, physics informed, physics guided. That will help me in my public defense in a couple of weeks too, because I use those different techniques, but I just group it all under physics informed or physics based. But yeah, so let's get started with this application. So as I present myself, I'm doing a PhD at LCAV, and my work is mainly on in a domain called computational imaging, which is how do we combine both hardware design and software for building vision systems. I guess the difference with computer vision would be, okay, you're just trying to work with a specific camera, a conventional camera, and then you're trying to do all these different algorithms of maybe classification, segmentation, whereas here we're really looking at both hardware and software. So what is lensless imaging? So maybe you don't think of it, but actually the first camera was actually lensless. I'm referring to the pinhole camera, if you're familiar with this. So the pinhole camera essentially was just a hole with no lens, and you would wait a long time essentially to form a picture on the other end of this hole inside a darkened room or darkened chamber. And as I mentioned, this would take a long time to actually form an image. So that was not practical at all. So the solution to that was, okay, let's increase the light, which means we make a bigger hole. But that means now we actually need a lens to help focus and bend those rays to form an image. So that's how we got to the cameras that are in all of our pockets that he's taking a picture of me with right now, but that are billions and billions of them. Another idea would be why not just poking more holes into that plane there. Sure, that would get more light, but the issue would be that we get what's called a multiplexed image. Now we are essentially going to get all these copies of the same picture on top of itself. But what we can do with lensless imaging, so the idea, if we come back, we're going to work with the hardware and the software, is if we know this pattern of the holes, we can undo that pattern algorithmically. So if we have a digital sensor on this side, we could use that information of those holes to then get back to a viewable picture. So here's kind of a side-by-side comparison of, let's say, that conventional camera where we use a lens to focus an image on that sensor, and then a lensless one, which would return this blurred picture, but then we use an algorithm to get back to it. Yeah.
So when you do this, let's say multiple holes,
Yeah.
do you account for parallax, or does that assume that you're taking an image of something that's sufficiently distant that it's not important?
So in the pinhole context, there's this notion of depth of field, which means that everything will be in focus. But it's true that, okay, when you increase the hole, you're going to have a much narrower depth of field. And whether you incorporate, let's say, this parallax depends on the model. So Keivan mentioned before about simplifying assumptions that you may make in your image capture process. So typically people, they'll just be concerned about what's in this depth of field region. So what the camera can capture. So I haven't heard of people accounting for parallax. That's a good question. It could be a direction of trying to improve some of the modeling. Yeah. So just to give some pros and cons of these two approaches. So, I mean, cameras work great. So why would you want to do this? Why would you want to get rid of a lens and poke all these holes and now add this extra step? So some of the advantages could be you can have a much more compact camera, and you can actually design cameras which have really arbitrary shapes. You can have a line camera, a bent sensor. You're not restricted to just having these two planes with a lens and a sensor. Another thing is that this mask can be fabricated at the same time as the sensor. So that's what I mean here by scalable manufacturing. Because usually you would fabricate both things separately. You would fabricate the lens, maybe with some more mechanical techniques, and a sensor with more chip fabrication techniques. Here you can do both all at once to have a much more scalable production. The aspect I look into my research, but I won't talk about it here, is this notion of visual privacy. So with these pictures we take, you can see it as like a first layer of encryption, where we're taking these pictures where unless you know the secret information of how this mask jumbled it, you wouldn't be able to decode this information. Some drawbacks, though, would be, okay, as you can see in this example, you'll get much poorer quality because the lens does one job really, really well, which is to focus light to form a picture. So essentially, we're throwing away that advantage it has. Another thing is we're introducing this reconstruction algorithm. So it could be slower or expensive, but this is where physics-informed machine learning can come into play to kind of improve the speed of those algorithms. And also light collection will not be as good as a lens because, again, we're getting rid of some of the advantages of using a lens. You have another question or no?
How many holes are in the mask?
So that's a parameter you could design. So that could be, if I follow his terminology, physics guided, maybe in machine learning, where you want to try to parameterize these physical parameters. So there's different types of masks, which I'll talk about actually. I'll come to that in just a bit. Yeah. But first, to talk about some applications of why would you want to use this type of camera. So as I mentioned, you can miniaturize imaging systems. You could use it for normal photography. With this type of camera, you can actually do in smaller scales for biological samples. You could do 3D imaging with a single image picture rather than trying to focus at different planes. In that similar vein, you can do computational refocusing, focusing at different depths. And then you can also, depending on the type of sensor you use, you could actually from a single picture reconstruct a high-speed video. Yeah, coming to your question on, okay, how do you design this mask? So there's multiple axes you could consider. So when I was showing this thing with the holes, that's what we would call an amplitude mask in this context, where we're trying to either block light or let light through. So we're modifying the amplitude of light. There's this other type of mask called a phase mask, where actually a lens, you can think of it as a phase mask, a specific type of phase mask. If you look at a lens, it's usually see-through. It's letting all the light through. And this bending of light, you can see of it as like a modulation of phase. So that's why we call it a phase mask. So we're bending light to focus it to form an image. So phase mask will be transparent, while an amplitude mask will have holes like we saw in that example, and maybe opaque regions which block light. In general, a phase mask is better because you're allowing more light to pass through. So usually people would prefer this. And let me just finish the other axis and we can talk. And the other axis, essentially, you can have programmable versions of amplitude and phase. Yeah, you have a question?
Does the phase mask change as the direction of sunlight?
So that's the point of the phase mask, that you're also going to be bending light. So a lens is one version of a phase mask. So it's like a specific version of a mask modulating camera. Any question?
You answered.
Similar, okay. Yeah, so in my work, I also look more on the programmable because there's some interesting things you can do there. So the other aspect is on the algorithm. So now we're going to get closer to the topic of this session. But just to kind of give some of the context and some of the underlying theory. So imagine we have a scene that looks like this, but we capture something that looks like this. So in order to go the opposite way, we call this an inverse problem. We want to go from what we've captured back to the underlying signal. And we would typically frame this as such an optimization problem that looks something like this, where we have y, our measurement. We have x, which we don't know, but we know that it goes through some, what we call a forward model, which we can model, which can be simplifying, as Kevin mentioned, as a linear system. So here we can show it as like a matrix vector product. And maybe we also add some regularization on top of this to kind of better frame this optimization problem. Maybe we add a constraint that we know everything should be positive valued since we're looking at intensities. But this is a classic formulation in, let's say, the more model-based approach, what we would call it. How many of you have seen this type of thing? Maybe like in a convex optimization course or imaging course? Yeah. So that's going to be kind of like our baseline approach. So on this forward model, so I mentioned, okay, we can think of it as a matrix vector product. We'll also typically assume that there's some additive noise because, okay, there's some imperfections at the sensor, some interferences. So if we can try to think of this H as we're trying, and I'll show a dummy toy example. We can think of this H where every row of H is trying to just do a combination of all the points in the scene to a point at Y. Or alternatively, we can think, and this is going to be a key term, is this point spread function. We can think of each column of H as something that's mapping each point in the scene to an image on this at our sensor, which is at Y. So to show this more graphically with the toy example. So imagine we have this green, we have this object here, 3D object. And what I'm doing is I'm just flattening out this object into a vector X. So for example, if we look at this green point, if we looked at a row of, or if we look at the whole X actually, to think of that first perspective, we can think of one row of H is just doing all a linear combination of this into a single point on Y. See this, hopefully? Or the other perspective I gave is, if you think about it in terms of the columns of H, this whole column of H, so this first point in X is going to multiply with everything along that column, right? So we can think of, if we only had 1 point in our whole scene, this P was mapping that 1 point, to our Y. And we can think of as the second column for the second point, third column for the fourth point, and so on. So each of these, we can think of it as a point spread function or PSF. Yeah.
So those are like the voxels in the original scene?
Yeah, so this X is you could think of it as a 3D volume, and then each individual box here is a voxel. Yeah.
And why would it be linear in the sense that maybe if something covers you up, isn't it like a non-linear? So there could be, but then we could think of it, if something's covering up, then there would be a 0 maybe in that point spread function.
But it's true that linear is a very big assumption that we're making, and it's something we have to simplify to kind of get to a more tangible, computational, be feasible, let's say, forward model, because we want to be able to compute this forward model efficiently, essentially. So actually, this one here that I'm showing is even too complicated. I'm going to make a simplification later on still. Peter?
Just two questions. So first one, when we work with applications, we actually work usually with 2D X, not 3D.
Yeah. So you mean in imaging context? So usually if we're like in a far field setting, like if I'm taking a picture of the guy on the computer there, I would think of it as a 2D problem. In those biological example, application I showed you before, there you would actually have variations along the depths. So that's where you would be interested in this 3D context. But in a more conventional imaging, you would only see it as a 2D. But you can generalize the 2D into 3D, where essentially your response for, let's say, your response for the green and red are just going to be 0, and you only are going to measure one plane because your lens is focusing at that plane. So I'm just trying to generalize your whole imaging of a 3D thing into this linear system, which again is still a simplification, but just to try to think of the 3D space.
And the second question is, why is always the same size as one plane of X?
No, it doesn't have to be. I'm just showing it in this example. Any other questions? Yeah, this is just a toy example to visualize what H is kind of doing. So one assumption that we'll often make, and actually he had this term LTI in his slides. Do you know? Are any of you familiar with what LTI means or LSI? Maybe I've seen this in an analyse course in the second year or something. Do you remember? Yeah, so linear time invariant. So in this case of images, we'll use a similar term called linear shift invariance. So linear time invariant is a long time, but since we're like in a 2D space, we'll typically talk about shift invariant. So one way we'll simplify this HX, because honestly, it seems simple, but actually it gets too expensive for a computer to have to compute such a model, is to assume we have a shift invariant system. So what we're going to assume is that instead of having one PSF per point, we're going to assume one PSF for all points. And just saying that if I'm shifting along the scene, it's just a matter of shifting my response. So I think there's a good visualization here. So let's say I measure a response right at the center. This is the response I get. The assumption I'm going to make is that if I shift down or up, this is just going to shift that response. So that's what this linear shift assumption is. And we're going to use that assumption to simplify this HX relation to essentially, so I'm going back to 2D here, this response P convolved with X. So that's what linear shift invariance allows us to do. And then maybe if you remember from your signal processing courses, we can do a convolution more efficiently in the frequency domain by taking the Fourier transforms of each component, and then we can just do pointwise multiplication in the frequency domain, and then go back to the spatial domain, or a similar thing in time. Any questions on that assumption, this assumption that we're making? Okay, cool. So that'll be an important part. And as Kevin mentioned, we need to make some simplifying assumption for our physics in our imaging system. But then that's going to cause some issues, but we're going to see, okay, how can we kind of massage those issues in a certain way? So if we come back to the problem, we had HX, now we can write it as this, where we have P convolved X. And this is also known as a deconvolution problem in signal processing or image processing applications. So again, to show the quantities, we have our X, which leads to Y. And then we need to be able to, let's say, explain or describe this P. So one way people describe it is by actually measuring this response. And the way you can do it is you put like you turn off the lights in the room, you just put a point source, like a white LED, you measure the response to that white LED, and you'll get maybe something like this, this is kind of describing how, in this case, it's a phase mask, so it's transparent, how that mask is bending the lights to get to Y. A normal PSF would just be a single point for a normal camera. In this case, the PSF is essentially the whole range of the image. So it's all spread out, which is why we get a completely blurred image. And then if we were to apply one type of algorithm, usually we would get to some cruddy looking picture like this. So no machine learning, just something like this. Still, you can actually make things up from this, which is quite impressive. But yeah, we'll see how we can make it better. Any question on the quantities in the back?
Yes, like I think it's very problem specific about how well posed this inverse problem is.
Yeah. So the mask will definitely affect how, so let's say the shape of this P or how this P looks will affect the ill-posedness. So what he means by ill-posedness is that you can get to just very, there can be many solutions that correspond to that one, to this problem. So you won't get, it'll be hard to get to a meaningful solution. So one way people deal with ill-posedness is by adding constraints, like, okay, it's going to be positive. Maybe I restrict the values of X to lower energies so that I can kind of massage the problem to something that's more, that's better posed. In case you're not familiar with that term, ill-posed. Yeah, it'll depend a lot on how you design your camera, which will affect that P. It's quite badly. I mean, if it was better posed, you would get a much cleaner reconstruction. Here, you get quite a few line artifacts because it's rather ill posed. And this is one on the better side of Lensa's cameras. There's some other where it's like really, really blurred images, or you get much more artifacts from the reconstruction algorithm. But it's definitely something to consider. And there, in ways you can quantify the let's say how well posed it is by trying to analyze this H matrix or this P. I won't talk about that here because I'll go into some other technical details. But yeah, but let's just assume that we have, let's say a purely signal processing, no machine learning approach to get to a reconstruction, and this is what it would look like. And essentially, we want to see now how can we push it towards these more data-driven solutions, as Kevin mentioned. All right, so let's go on forward. So one approach to do a more signal processing approach, so actually not going fully to the machine learning yet, is something called Wiener filtering. How many of you have heard of this technique? Okay, cool. So essentially the idea is that we're going to minimize this mean square error in the frequency domain. And there is a closed form solution for this, essentially. So it's a quick way of getting a solution, but a quick way to get to a really cruddy solution, to be honest. But it's essentially the filter in the frequency domain will be given by, just take this quantity as it is. It's like the complex conjugate of the PSF in the frequency domain kind of normalized. And this is essentially a filter which will minimize this mean square error. So then you can get a one-shot statement for that image estimate. So maybe if you haven't, I didn't say it explicitly, but when I put this hat, it means like an estimate of X. Another approach is to use iterative algorithms to get to an image estimate. So we can use gradient descent, which maybe you're familiar with more in machine learning context, actually to get to an estimate of the image. So the way we essentially derive it is, again, we take the gradient of this and we want to move in the opposite direction of the gradient. So we take the gradient, we set it to 0. Okay, that's how we got Wiener filtering. But in this case, we're going to start with an initial estimate X, and we're going to move in the opposite direction of that gradient to hopefully minimize this cost function here. So that's an iterative way. So unlike Wiener filtering, which gives you a single shot, this is going to take a bit more iterations, but generally you can add some more constraints to get to a better solution. Let me skip parts of this. So just some of the notation here. This HH is what we call the adjoint. I'll just use that word, but you don't need it. I'll just skip ahead. So on top of gradient descent, one way we can add some prior information is by applying a function on top of each estimate. So that's what we would call projected gradient descent. So I just went through those quickly because now we're going to see. So if just keep in mind, there's Wiener filtering, which gives you a single shot way, and we have a closed form, and then there's these iterative techniques. So now we're going to take these two techniques and essentially look at how we can use data to actually better tune those techniques. So just coming back to the theme of physics informed. So we had our approach was we had an image, we have a PSF, and we're going to think of that, that minimization problem I showed you before as this camera inversion block. And either we could use Wiener filtering, as I showed quickly, we can use gradient descent or projected gradient descent. FISTA is one version of that projected gradient descent. ADMM is similar to gradient descent. And it gives you some estimates, which we saw was not so great. So what we're going to do is if we take this Wiener filtering, so this left-hand side, one assumption that we made is that we had a good PSF, but maybe this PSF that we measured is not perfect. But with some data, so I think the term here would be in your terminology, physics guided. We have some data. We're going to try to improve our PSF to make it better fit to the data that we have. So we're going to tune the PSF. In these iterative techniques, so usually when you do gradient descent, you have these step sizes. So what we're going to do is we're going to learn the best step sizes at each iteration. And instead of running maybe for 100 iterations to converge, maybe we only need 5 iterations to converge. So it can drastically decrease the time to get to an image estimate. And then from data, we're essentially going to learn those parameters. And how do we do that with data? Similar as any supervised problem. So we have some ground truth data, which we're now going to feed to a loss. And here this is just 2 terms that we may have in our loss function, but we don't need to worry about those. So just imagine you have a loss function, and we're going to back propagate to that camera inversion block. So for the Wiener filter, that means we're going to back propagate to update what we thought was the PSF. And in this iterative technique, we're going to back propagate to update what we maybe manually tuned as the step size for gradient descent. So in that way, we can improve the quality of just this plain camera inversion block. So that's already a quick way to get some sort of physics enhanced approach. Any questions on this? Because now we're going to build on top of that. Okay. So one thing that we did in our work was actually, I think the word you used in this case was the union of the two. What was it when you used data-driven and physics? What do you call it? Encoded. So now I'm going to do a physics encoded. So I'm using the terminology I learned, where I'm going to actually incorporate neural networks before and after this camera inversion. And essentially, I'm going to do the same process where I have my loss function, and I'm going to back propagate to now update the parameters of this is a neural network, this is a neural network, here's a neural network, but also these physical parameters that are inside the camera inversion. And then here I can just show you a difference of how much improved the quality of the image can get. So you can get huge improvements from now adding these neural networks in the right places. And why do we add those neural networks? So now we need to describe, okay, we can't just throw them where we want, but it's good to have some intuition. So let me give you some basic intuition. So we mentioned about how that we made this simplifying assumption of shift invariance, right? Where ideally we have a unique response for each point, but what we did was we said there's one response for all points. So now let's see, okay, what is the impact of doing that simplifying assumption? Because actually one other lab, so from Berkeley, they've measured, if we take that response from the middle and we try to measure the similarity between the responses as the angle gets wider and wider, we see that we start to get this decay. That, okay, within 37 and minus 37 degrees, so like a field of view like this, we get a pretty good similarity, but we can see it starts to drop. So we're essentially introducing error into our forward model by making this simplifying assumption. And then we can think of this, we can model this error as we have this, what we expect to be a real H, but by using P, we are adding some noise now to our forward model. So just to see how this kind of breaks down. So if we did a basic inversion approach, so don't worry if this goes over your head, this is a bit of math here. Imagine if we used the perfect H, we would just get X. But since we're adding noise now to this H, actually we're introducing some noise terms. And the main idea is that, okay, by having this simplification, we're amplifying the input noise, and then we're also introducing noise at the outputs. So the intuition of this modular approach is that we want to minimize the noise that is going to inevitably get amplified. So that's why we put the neural network before the inversion. We already talked about the camera inversion, which through physics enhanced, physics informed, we can reduce this mismatch by, for example, fine-tuning the PSF. But we're also going to add, the reason for this post-processor is also now to address this residual error, but also this new error we've introduced into the problem because of making our simplification. That's why those different blocks come up. But yeah, just to give you the side-by-side comparison. So we had that model base, which was just trying to solve that optimization problem. We can incorporate those physical priors, but it can be slow to converge. Good thing though, it doesn't need any training data. Whereas with the physics informed, now we can incorporate those physical priors. We can bound the compute, so maybe we need fewer iterations, but some of the drawbacks is that we need that training data, and it can still kind of break down to unseen data distributions. But hopefully it's more interpretable since we broke it up into those modular components, and we also tried to add those neural networks to address other types of error that pop up. And I guess to the right side would be like your naive neural network where you just throw input-output pairs, but you don't incorporate physical priors. So just to show you some results. So here is a data set that was collected with that PSF that we saw before. This is the raw data, so the completely lensless blurred data and the corresponding ground truth, which was measured with a real camera, like in this type of dual setup. You don't need to do this type of dual setup. It was just done for this data set. And so we can see some metrics here. So if we just do that pure ADMM approach, which is the model-based, from there, we essentially get like a 10 dB improvement. So you can think of 3 dB as like a doubling of improvement. So every 3 dBs, we're doubling more. So here we like 2 times 2 times 2 to almost get to 10, 8. We get like 8 times better performance almost here. And this is from, and so these two lines are just showing, because this was in a research in our paper where we're trying to show the benefits of having this preprocessor. So using both the pre and the post processor is better than just only doing a post processor neural network. So there's just some visual results like we saw before. So this is kind of what ADMM would give, really kind of blurry, kind of not super well detailed. And we have much better details, for example, on the cake and whatnot. And then as Kayvan mentioned, we also want to see how our performance is when we add noise to the situation. So here we're just again showing how using the preprocessor, if you remember that intuition, because of this mismatch, we're amplifying input noise. So the role of that preprocessor is to remove the noise before amplification. So here we get better robustness. And also we were talking about this delta H, which gets added. So before we were adding this in this modular approach, we were adding this PSF correction to kind of correct for the probably wrong PSF that we have. So essentially here we're showing if we intentionally add noise through our PSF and try to do a reconstruction with it, the other approaches would break down, but incorporating this component into our, say, modular reconstruction can give better robustness when we have more mismatch in our PSF. But yeah, those are just some results which just kind of convey the message, as Kevin showed with his results, of how incorporating physical information or where noise can come from can provide better robustness and generalize. So for example, we didn't train in these other noisy contexts, but how we can better generalize to these cases where we kind of deviate from ideal situations. So to conclude, so this is a figure I had, so I just submitted my thesis recently. So essentially we have our classic approaches, don't need any training data, but could be slow. What we're trying to move towards is incorporating some machine learning. This can allow us to bound compute, but it can require data, but be less interpretable unless we add some of this physics informed. There's something in between where we can actually use unsupervised techniques, which I didn't cover here, or pre-trained models. And there's another axis to this whole thing where actually you can use the hardware itself in the learning process. So you can actually, if you're able to, let's say, query your input system, instead of having a simulation for your forward model as we did, you can use the physical system itself to get measurements. You tweak the parameters of your measurement system, get a new measurement. So that's kind of these more hardware-based techniques, or what I call hardware in the loop techniques. But yeah, you can, I guess, check my site or Google Scholar if you want to see such techniques. So any questions? So now we're going to move to the what's next step. Any questions on what I've presented on how to incorporate? Yeah.
So the training time it's more expensive to train this.
Exactly. So like you said, since we have this simulation within our system, it's more expensive than just training like a off-the-shelf UNet or ResNet, because now we have to do that convolutions each time. But that's why we had to make that simplification to shift invariance, because if we had to do a more complicated forward model which tries to have the full H matrix, it'll be way too expensive. So at least shift invariance can simplify it, but it's still more expensive than just doing a simple UNet.
And the inference is more expensive, like you get.
Yeah, inference is also going to be more expensive than just a plain neural network, but you can get better robustness, generalizability. Yeah. Any other questions? Yep.
The inference being more expensive. All the
So so inference is more expensive. It's not only on the in this case, I don't add back I forget what you called it in your terminology. You were adding some physical thing to the loss. My loss wasn't doing that. Unless there in some cases I would add something here for some more physics informed loss. But the reason why inference is expensive, because you can think of, let's say, the naive approach as only having the post processor. And now we're introducing all these other components, and this is the one that's most expensive of them all because of doing either this unrolled ADMM, which has 5 iterations, or even Wiener filtering. You can think of it as 1 iteration, but here we're incorporating we're doing a convolution, which means we have to go to a frequency domain and back. So that's why inference is more expensive. But at least what we could show is that if we, let's say if we have a budget of model parameters, like in our experiments, we would limit ourselves to 8 million model parameters. What we could show is that if we put all those 8 million into just only using a post processor for naive, or if we split it among all of these, it was better to do the splitting among with the physics informed. So, any other questions? Okay, so what's next? So here we're just going to kind of do some selfless promotion of our labs and projects. You want to talk on the slide?
Okay, for the last part of my presentation, I just want to promote some openings that we have in the lab. So if you're looking for the semester project or master thesis, feel free to check our website. And now you can take a look at the different topics that we covered, for example, from physics informed graph neural networks. For example, I don't know if you are interested on working on at the intersection of the physics, machine learning, or building energy model, you can go and apply for this position. Or if you are more likely go into the computer vision, you can check, for example, it's about I don't know, robust multimodal 3D reconstruction. And also we consider some different topics also in the generative AI. I don't know how many of you are familiar with the diffusion models, but recently we want to go for this direction and using the diffusion model for the industrial assets, for example, again, the distributing network, electricity, or different kind of stuff. And yeah, feel free to send the email. And also, yes, thanks for coming and attention.